Today it's my pleasure to present to you Floraine Berthouzoz. Floraine is from Switzerland. Comes to us by way of Berkeley, where she's finishing up her Ph.D. She's a prolific researcher, has done a span of projects that touch on numerous areas, including graphics, visualization, HCI, a bit of vision, machine learning, and signal processing as well. And today she'll talk about some of those projects. Floraine.
Thank you, Brian, for the introduction, and thank you for having me here today. So as Brian mentioned, over the last couple of weeks, I've done a lot of work on teaching people procedural instructions as well, and in particular, my work focuses on photo manipulation procedures. So I would like to show you some of this work today in this talk. So in general, I'm interested in understanding how we learn, and I think many of us are probably interested in this question. And over the last couple of years, we have seen some major changes in the way people access instructional material. Sites like the Khan Academy offer thousands of courses online, and millions of students take them. So one of the nice benefits of this is that it makes education accessible all over the world. And computer science has played a very active role. And computer science has played a very active role in building the platforms that support this kind of learning. In fact, the three main platforms all started out of computer science departments. And they're designed to teach all forms of knowledge. And there are many different types of knowledge. There's factual knowledge, conceptual knowledge, procedural knowledge, and metacognitive knowledge. I've been particularly interested in procedural knowledge, since it's the foundation of so many engineering tasks that we all have to perform on a daily basis. And so procedural knowledge describes the sequence of steps that are required to complete a task. For example, the steps required to take the derivative of an expression, or the steps required to manipulate an image. And so let's look at cooking as an example of a procedural task. So a few years ago, I got interested in molecular gastronomy, and what you see here is a watermelon that has been turned into a gelatinous sphere using a process called spherification. And so one of the questions I got interested in is, how do we acquire the procedural skills required to cook such dishes? And it turns out there's been a lot of work on this in education and psychology. So this is one model that they have developed. And so let's look at these three stages, sticking to the example of cooking for now. So the first stage is the cognitive stage, where learners follow step by step the instructions that they are given. So in this spherification recipe, the steps are clearly described. And so following the steps requires conscious efforts and leads to high levels of cognitive activity. In the associative stage, learners start synthesizing and comparing the information across multiple recipes. So here, I would make a conscious effort to understand the similarities and differences between these spherification techniques. And in the last stage, the autonomous stage, the learners have now acquired the procedure and can transfer their knowledge to new tasks. So for example, after I learn how to spherify watermelons, I can use the same sequence of steps to spherify cherries or olives, for example. And so in this stage, learners also become experts. They can do the task fluently without effort and can adapt it as necessary to new ingredients. So at this point, the learner could just open the fridge and make a new molecular dish. Personally, I'm still trying to reach this stage. And so for cooking, there are lots of recipes online. For example, food.com has almost 500,000 recipes on their website. But people are now sharing instructions in the form of step-by-step tutorials for many different kinds of tasks. For example, sites like WikiHow or Instructables provide instructions for assembling and repairing physical objects. There are also many sites that provide tutorials for making crafts. And of course, there are lots of sites that teach people how to use software. And the three-stage learning model really applies to procedural tasks within all of these domains. But for each of the stages, there are a number of open challenges that we should address in order to improve the learning process. So for the cognitive stage, a major challenge is to facilitate the authoring of high-quality instructions. So as we'll see in a moment, tutorials are typically hand-designed and are very time-consuming to make. For the associative stage, a challenge is to enable the comparison and browsing of multiple tutorials. So currently, there are no interfaces that allow you to compare sequences of operations. And after learning a procedure, a person often repeats it over and over again. And so for procedures that are time-consuming and complex, this can be a bit tedious. So a challenge for the autonomous stage is to automate the transfer of procedures. And note that here this challenge is about teaching a procedure to a computer, whereas in the two previous cases, it was about facilitating the learning process for a person. And so in the work that I will show you today, we will address these challenges in the context of photomanipulation procedures. So with tools like Photoshop, people commonly adjust skin tone, enhance sunsets, apply digital makeup, and perform many other kinds of manipulations. And typically, they learn these manipulations from tutorials that they find on websites and in books. In fact, photomanipulation tutorials are the most common form of software tutorials shared online. And so to address the challenges that we just saw, I built 3 different systems that I would like to show you today. So first, I've developed a tool to automatically generate high-quality step-by-step tutorials from a demonstration. And so with this tool, making tutorials becomes really fast and easy. I've also built a new interface for browsing and comparing tutorials. So this allows learners to better understand the similarities and differences between multiple photomanipulation procedures. And finally, I've automated the transfer of several classes of photomanipulation procedures. So let me start with the first project on automatically generating photomanipulation instructions. So here's an example tutorial, a well-designed example tutorial for changing eye color that I took from a book by Huggins. And so researchers have shown that several characteristics make these tutorials particularly effective and thereby facilitate the cognitive stage of the learning process. So for example, they organize the operations into steps, and a person can choose to look at an overview of all the steps or a particular step in more detail. And every step contains a text description and annotated screenshots. And the text often explains how the operation is going to affect the image, which then is useful information if the person wants to transfer the operation to a new task. But the big problem with these tutorials is that making them is very time-consuming. So you need to save all the relevant screenshots, you need to add the annotations, you need to write the text descriptions, and then you need to lay out the tutorial. And all of these steps takes a really long time. So sadly, as a consequence of that, many of the tutorials that you find online are not well designed. So for example, in this tutorial, it only shows a before and after image for the manipulation, but doesn't show any of the images for the intermediary steps or for the widget that a person has to use. And the alternative is to simply provide screen capture videos like these ones. And so these are incredibly easy to create, but research has shown that they're far less effective than static tutorials because they force the person to work at the space of the video rather than at their own pace. Nevertheless, because they are so easy to create, they have become incredibly common online. And so this work really grew out of my personal frustration for how many low-quality online tutorials there are. And so the goal for this project was to automatically generate high-quality static tutorials that facilitate the cognitive stage of the learning process. And we want to generate these tutorials from a single demonstration and thereby make them as easy to create as video tutorials. So here's our approach. So given an input image, a user first demonstrates the manipulation using an instrumented version of GIMP that records all changes to the application state and interface state. And in parallel, we run a set of computer vision-based labelers to recognize semantically important regions in the image. And then we use these labels and recording to automatically generate the tutorial. So as a user demonstrates the operations, we record both changes in the interface state and in the application state. So for example, here, the interface change corresponds to a slider move, and the application change corresponds to setting the contrast parameter to 20. And we really need both types of information to properly interpret and visualize the demonstrated manipulation. The user then clicks the OK button to commit the changes. And we also take screenshots at every mouse click, mouse release, and key press. So here's the whole recording for this manipulation. And these recordings are typically, so here already every interface change has been associated with every application change. And as you can see, these recordings are typically very long and contain a lot of unnecessary steps. So our goal will be to clean up the recording and simplify it by grouping the steps. So we start by eliminating unnecessary operations such as undos. And then we group together consecutive changes to an application state to generate a succinct sequence of steps that each involve one major operation. So we start by segmenting the recording into operations which are delineated by commits. And then we group changes to the same parameter within an operation. So for example, here we group both brightness changes and both contrast changes. And so we use program analysis techniques to determine how to do the grouping. So in this case, we find that we should be doing the grouping, that the grouping is absolute, meaning that we should discard the intermediary settings of the parameters and simply maintain the last value of the parameter. We also group consecutive operations. So for example, here the person executed twice the brightness contrast operations and multiple times the dodge operation. And so in this case, program analysis tells us that the grouping is relative, meaning that we need to accumulate intermediary values to then compute the last value of the parameter setting. And so as you can see, after the grouping, we have a much simpler step-by-step presentation of the manipulation, where every group now can be rendered as a step in the output tutorial. And so here, this recording would correspond to 3 steps in the tutorial. And our recording also includes screenshots. And when generating the tutorial, we add annotations to these screenshots to illustrate the task the user must perform. And we render these annotations based on the position information that we record with each change in the interface state. We use a template-based approach to generate the text descriptions for each step. For example, here is an example template for the selection operation. And here the green variables are based on application and interface level information, and the blue location variables are based on semantic information that we extract from the image. So just to remind you, when we first load an image, we run a set of computer vision-based labelers on the image to identify semantically important regions. And more specifically, we recognize facial regions such as the eyes and the nose, as well as the sky and the ground of outdoor scenes. So we then use these labels to fill in the blue location variables in the text descriptions. So for example, for changing eye color, the text might say, use the ellipse select tool to select the iris. So the final stage is to lay out the tutorial. So we use a grid-based layout, and we divide the space into columns, and then stack the steps vertically in each column. And each step contains a text description on the left, an annotated screenshot in the middle, and if there's a visual consequence to a step, we add another screenshot of that consequence to the right side. So this is the complete algorithm, and let me now show you some results. So we used our system to generate 8 tutorials, including 6 portrait retouching techniques and 2 methods for editing outdoor scenes. So here's an example tutorial that teaches you how to remove the bags under the eyes of a person. So in the first step, we ask the user to select the heel brush, and we highlight the heel tool in the toolbar. Next, we ask the user to set the anchor point for the heel brush, and again, we highlight the selected point in the image. And finally, we ask the person to paint under the eye of the person, and note that we highlight the paint strokes in yellow, and we use the labelers to determine that the person should paint under the right eye. And the right side image here shows the visual consequence of performing that step. And here again is the full tutorial. Here's another tutorial that teaches you how to enhance sunsets. It has 3 pages and 13 steps. In the second step, we ask the user to select the sky. And again, we use the labelers to determine that it's the sky that the person needs to select. We then ask the user to paste the content of the clipboard, meaning the sky, and we highlight the new layer that appears in the layers palette as a consequence of this step. And finally, the last step teaches you how to change the hue, saturation, and the lightness of the image. And note that we group both slider changes into a single step. And here's the full tutorial again. So we ran a user study to determine if people would be able to follow our automatically generated tutorials. So we compared our tutorials against hand-designed tutorials from a book and narrated video tutorials. And we asked each subject to follow 3 tasks of increasing difficulty and to apply these tasks to new images that we gave them. And so for each manipulation, they either used our tutorials, the book tutorial, or the video tutorial. And so overall, we found that users were 20 to 44% faster using our tutorials and committed 60 to 95% errors. And note that the red bars here represent our tutorials and lower bars are better. So as we expected, we performed better than screen capture video tutorials. But we are actually quite surprised that we also perform better than hand-designed tutorials. And so we believe that this might be because these hand-designed tutorials, book tutorials, usually provide more explanations, but they also tend to eliminate some steps. So for example, it would ask the user to select the sky without actually providing a screenshot of how to do the task. So we conclude from the studies that users are able to follow our automatically generated tutorials, and thus they support the cognitive stage of the learning process. And so as future work, I'm interested in understanding how people can use our tutorials for transfers. So for example, I would like to give people a tutorial on eye whitening and see if they can perform a similar task like teeth whitening. And so doing transfer with our tutorials can be very challenging since our tutorials only tell you what you need to do and not why. So for example, here it tells you to add a point to the curve, but you actually have no idea whether this point is necessary in the first place. So one solution may be to provide additional interfaces that allow the tutorial author to enter this additional information. And so finally, we also plan to implement a feedback mechanism so that we can let the user know if they deviate from the instructions. So this will require us to track the user as they're performing the task and also decide for each step whether they executed it correctly or not. It might also require modeling the typical types of errors that people do and helps them get back on track. And so one of the really exciting parts of this project was that I was able to work with Wilmot Lee and Mia Doncheva at Adobe and help them transfer this research and put it into a commercial product. And so this was a 1-year collaboration, and based on this work, Adobe recently launched Photoshop Tutorial Builder and Player. And so these are 2 products that allow users to record, to generate a tutorial by demonstration, as well as directly invoke commands from the tutorial. And so people have been very excited about the software. In fact, it's been downloaded 60,000 times since last May. And so it's really exciting for me to see how many people are interested in using the software to create their tutorials. So after building the tool to generate tutorials, I became interested in helping people navigate and compare multiple tutorials. And so these comparisons are really essential for the associative stage of learning. So as you have seen earlier, websites like goodtutorials.com describe tens of thousands of photo manipulation procedures. But currently, the only way that people have to navigate this collection is by paging through long lists of tutorial titles or by performing keyword search. And so here's one of these tutorials that teaches you how to recolor the hair towards a reddish or brownish color. And in the first step of this tutorial, the user needs to execute 6 different Photoshop commands. And the commands are crucial, and properly following the tutorial requires executing them correctly. But the user has to very carefully read the text in order to identify them. And in addition, it is very difficult for people to compare the workflow of several similar tutorials. They would have to manually identify the commands within each tutorial and then carefully compare the sequences. So in our work, we use a text analysis approach to automatically identify the commands within the tutorial. And so more specifically, you use a naive-based classifier and Witten-based smoothing to obtain good results with a small and sparse set of training examples. And so once we identify the commands, we simply look up the equivalent Photoshop operations. And so here's an interesting example. So the command soft flake brush in this tutorial actually encapsulates 3 different Photoshop operations. And so in this case, our algorithm automatically identified these 3 operations. And so we extracted the commands for 2,500 tutorials that we downloaded from the web, and we obtained an average accuracy of 95%. And so based on, we use this command level structure to build Sifter, a faceted browser that allows users to organize, sort, and filter this collection based on commands. And so filtering facets include the tutorial category, the command name, and also the length of command subsequences. And so for each tutorial, the browser also includes a table of commands that summarizes and indexes the tutorial. And finally, the browser provides an alignment view, and that is designed specifically to help people compare multiple similar tutorials. So let's go back to the hair recoloring example. So it turns out that there are lots of different Photoshop procedures to do this task. In fact, our collection contains 7 different tutorials on this task. And so we can use the alignment view to compare these tutorials. So here, each column represents the command sequence for the tutorial, and we color code similar commands. So for example, all brush commands are colored in yellow. And the sequences are also aligned with one another, and we draw lines between identical commands in different columns. And so in this view, we can quickly see that the first 2 tutorials use a similar approach. They share a lot of the same commands, and there are a lot of edges between them. And they primarily use the brush tool to do the hair recoloring. And similarly, these 3 tutorials are also very similar. Again, there are a lot of edges between them, and they share a lot of the same set of commands. And here they primarily use the fill command to change the hair color. And it's only this last tutorial that takes a very different approach. As you can see, there are no edges between these tutorials and any of the other tutorials, which means that it doesn't share any commands with them. So overall, this alignment view allows us to determine that there are 3 main approaches to do hair recoloring, where the approach of tutorial 4, 5, and 6 seems to be the most common one. And so being able to compare the tutorials in this view allows learners to build a model in their head of the different ways a task can be done. And so to evaluate Sifter, we asked 10 participants to perform various navigation and comparison tasks using Sifter, as well as keyword search. And so keyword search was simply the Google search interface that was limited to our tutorial collection. And so not surprisingly, participants were more successful and accurate when using Sifter. In fact, they abandoned 30% of the tasks when they had to use keyword search. And so by offering these additional tools, Sifter makes tasks like comparing tutorials really easy, which can really help with the associative stage of learning. And so the third project that I would like to tell you about is about automatically transferring photo manipulation procedures to new images. And so this has been a really fun project to do. It's actually one of my favorite projects, and I think you will see in a moment when you see the results why it's been so much fun to do. So note that in this case, our goal is to teach a procedure to a computer, whereas in the 2 previous cases, it was about facilitating the learning process for a person. And so consider this skin tone correction manipulation. So here the photographer removed the blue cast from the skin. And in some cases, the same manipulation must be applied to a large collection of images. But manually transferring the same sequence of operations to every new image can be very time-consuming. And so tools like Photoshop let users record macros that encapsulate the sequence of operations and parameters that are required to complete the task. And once recorded, the macro can be applied to every new image with a single button click. So you may also be familiar with the red eye correction tool or the Instagram filter, and so these are examples of today's macros. But the problem with current macros is that they're very basic and they cannot adapt to the content of the image. So for example, here, this macro does not adapt to the new location of the skin. And in addition, transferring the location of selections is usually not enough. So the parameter set for this dark-skinned person make the pale man look very yellow. And so the goal of this work is to make macros content adaptive by learning the spatial and operational parameters from multiple demonstrations. And ideally, we would like our system to work with all kinds of manipulations. So to better understand what types of manipulations people commonly perform, we surveyed 151 tutorials that we downloaded from the web. And we found that 30% of these tutorials describe global manipulations that are designed to operate on the entire image. 26% focus on faces, 18% on landscapes, and the remaining 26% are about a much wider variety of elements. And so in this work, we are focused on the first 3 classes of photo manipulation tutorials. And so these make out 74% of the manipulations that people commonly perform. And so here's a manipulation for each of these 3 categories. So the Lomo manipulation at the top darkens the corners of the image and also increases the contrast in the image. The makeup manipulation in the middle is an example of a face manipulation, and the landscape manipulation at the bottom, the dark sky manipulation at the bottom, is a landscape manipulation. But in all 3 categories, current Photoshop macros fail to properly adapt to the content of the image. So the leaves are way too bright, the makeup is in the wrong position, and now the Sphinx had its entire head cut off. But if we given a small set of training examples, our content adaptive macros can properly transfer the manipulation in all 3 classes. And so our results now look very much like the ground truth images. So I will start by showing you how people would use our system and then describe our implementation. So here we will demonstrate a lip gloss manipulation. And in addition to the typical Photoshop windows and panels, we provide a labeling correction panel that lists all the facial features that were recognized by an automatic face detector. And so as a user is selecting a region in the Photoshop, our system recognizes it at the upper and lower lips and checks these labels in the list. So the panel provides feedback showing that our system properly interpreted the selection. So next, the user adjusts the hue, saturation, and color histogram of the lips. And note how the color of the lips now changes. And the final step is to just paint a highlight stroke on the lip. And so after the user performs the first demonstration, our system creates a macro application panel that shows how the image appears after each step of the manipulation. And so when the person encounters a new portrait that he would like to apply lip gloss to, he simply selects the lip gloss macro from the list of recorded macros. And so the panel now shows the result of automatically applying this macro to this new target image. But after only a single demonstration, the result is likely to require some corrections. So here we immediately see that the first step is incorrect, and the lips are in the wrong position. So the user clicks on step 1. And again, you see that the selection is not at the right location. So the user goes ahead and corrects the selection. And then he switches to a labeling correction panel and checks the upper and lower lips to associate these labels with this new selection. He then switches back to a macro application panel and simply propagates the changes. So now the user is pretty satisfied with the adaptation, and our system, our framework, treats each corrected macro as an additional training example to improve the quality of our macros. And after 4 demonstration, we run a leave one out cross-validation to estimate the macro's robustness. And so for every new target image, the panel displays the average error for each step. And we highlight high values in red so that the user immediately knows which steps may require some corrections. And so as the user adds more training demonstration, the macro becomes more robust and error values decrease. And our experiments indicate that our macros produce consistently good results after about 20 demonstrations. So let me now tell you how this actually works. So we first record a macro demonstration, learn the spatial and operational parameters, and then apply the learned macro to new images. And to learn the parameters, our system combines machine learning with image recognition. And so we use the same 2 labelers that we used before to recognize facial features, as well as the sky and the ground of an outdoor scene. And now we also add a 3rd labeler for skin detection. And so Photoshop provides access to a wide variety of operations. And one of our main observations is that all of these operations fall into three main classes. So there are image processing operations that modify all the pixels within a selection, such as the blur filter, for example. There are selection operations to specify an image region. And there are brushstrokes operations that select a region and modify the pixels within it. And so to adapt an image manipulation to new content, we need to develop new algorithms for adapting each of these three classes of operations. And so let me just give you a flavor for how we do that. So to adapt the parameters of image processing operations, our goal is to compute a set of features f on the image, and then build a mapping between the features f and the output parameters y from the training demonstrations. And so we assume a linear model, and the key problem is now to estimate the coefficient c from the training features and the training parameters. And so we use least angle regression to do this estimation. And so for the learning to work well, we need to pick a set of features that correlate with the parameter values. So we use pixel-level features such as the color, the contrast, and the luminosity histogram, as well as label-based features that are based on the labels that we computed on the image. And so note that our features are different for adapting image processing parameters, selections, and brushstrokes. So to adapt selections, we form a feature vector for each selected and non-selected pixel. And then when we classify each pixel of a new image as being selected or non-selected using naive Bayes. And so while this method is very simple, we will show in a moment that it works quite well for our examples. And so finally, let's look at how to adapt brushstrokes. So a brushstroke is composed of a brush region and a stroke path. So the brush region limits the area that's affected by the operation, and we adapt it in the same way that we adapt selections. To adapt the stroke path, we use a Markov chain model with three states: the start point of the stroke, the intermediary ith point of the stroke, and the end point of the stroke. And so once we set the start point of the stroke, the next position only depends on the current position. So given a previous point P on the stroke, we compute a table of transition probabilities to all of its neighbors Q. And then we pick the Q as the next point that maximizes this transition probability. And we provide a lot more detail on the stroke transfer in the paper, where we also describe how we can compute multiple strokes within a brush region. So let me now show you some results. We tested our approach on 20 manipulations in the three most common categories, meaning global manipulation, landscape, and face manipulations. And so as you can see, for each of these manipulations had a number of selection, stroke, and parameter operations. And we always use 20 training demonstrations, and we tested these manipulations on 50 to 100 images. So let me start by showing you some fully automatic results for global manipulations. So here's the low-mo manipulation that we saw earlier, where we darken the corners of the image and increase the contrast. And so this is an example of a training demonstration. Here are some new target images that we would like to apply this manipulation to. And here are automatic results. So as you can see, our markers correctly applied the vignetting and increased the contrast. Let me just switch back to target again. And our results. So here's another example of a reflection manipulation where we reflect the object onto the background. And so note that this manipulation assumes a solid background color. Here's some new target images. And here are automatic results. So these images were correctly reflected, the objects were correctly reflected onto the background. And note that this manipulation was applied with a single button click. So now let me move on to some landscape manipulation. So here's a waterfall manipulation where we smoothen the water as if we had had a long exposure. Here are some new target images. And here are automatic results. So as you can see, the water now appears to be smooth. Let me just switch back to the target and our results again. And note that we don't have a waterfall detector, but because of the white color of the water, we are able to properly transfer this manipulation. So here's another landscape manipulation where we add snow to the scene. Here are some new target images where I wanted to see what San Francisco would look like with snow. And here are automatic results. So the last category are face manipulations. So here's a makeup manipulations where we applied colored lines above and below the eye. And note that this manipulation requires very precise brush strokes. Here are some new target images. And here are automatic results. And the lines now precisely follow the contour of the eyes. Let me just switch back to the target and our results. And here's one final example of a mustache manipulation. Here are some target images. And here are automatic results. So I've shown you some examples, and it works fairly well, but of course there's some failure cases. So here, in the first example, the learning fails to correctly adapt the parameters for the contrast manipulation, or it thinks that the white grass should be selected as the waterfall, or it applies the mustache and the makeup at the wrong location. And so to evaluate our framework, we conducted a study using Mechanical Turk. We picked 7 manipulations and applied these manipulations to 50 to 100 images. And for each manipulation, we created 3 different types of outputs. A ground truth image where we manually applied the manipulation to the image, an average image where we averaged the training parameters and simply copy the brushstrokes and selections. And so note that the average image is slightly more sophisticated than what current Photoshop macros can do, and our automatic results. And so the goal of the study was to see how similar our automatic results look to the ground truth images. So we put up 4 images on Mechanical Turk, with the ground truth always being on the left. And then we asked people to rate how close the images D, E, and F look to the ground truth image, where 1 was indistinguishable and 5 means that there's a large difference. So the images D, E, and F corresponded to the average image, the ground truth image again, and our automatic results. And we randomized the order of these 3 images. And also, remember that users don't see any of those labels. So here are the results. The x-axis indicates the 7 manipulations, and the y-axis indicates the average user rating. And remember that lower bars are better. We found that our automatic technique is given significantly higher ratings than our strawman, the average result shown in green. And it's also given ratings that are similar to the ground truth ratings shown in red. In fact, in 47% of the cases, people rated our results as better or equal to ground truth, meaning that I really couldn't see a difference in them. And the study therefore shows that we are able to successfully transfer many different kinds of manipulation. And so while this does not improve the learning process for a person, it removes some of the tedium of having to apply the same task over and over again. There are several directions for future work. So our macros can currently transfer manipulations like eye recoloring to different images of the same task. And so in psychology, this is called near transfer because the tasks are very similar. But what our macros cannot do is a far transfer, that meaning applying the procedure to tasks that appear to be very different, like wall recoloring, but yet share a lot of similarities with the original task. And so using interactive machine learning approaches, I'm interested in building macros that can do some of the far transfer. Also, earlier we described a method to automatically generate tutorials from a demonstration. And so tutorials provide you with the sequence of steps, but a person still has to do everything themselves. And in contrast, a macro does everything for the user, but the user also doesn't learn anything. And both tutorials and macros are useful depending on the context and the goal that the person has in mind. But there's also a tension between teaching someone a new skill versus just doing it for them. And so one of the questions that remains is, are there places in between where we can automate some of the components, and would those be useful? So I've shown you 3 different systems. The 2 first ones facilitate the learning of procedures for a person, and the last one is about teaching a procedure to a computer. And I believe that there are several takeaways. So first, we found that we can combine program analysis techniques with computer vision to generate high-quality software tutorials. And so our tutorials are very simple. They contain no explanations, but people are still able to follow them, which is actually quite remarkable. And so this technique has the potential to significantly improve the quality of software tutorials shared online. We also found that using natural language processing techniques, we can extract the underlying command level structure from tutorials on the web. And we can build new interfaces that allow people to navigate, analyze, and compare multiple large collections of tutorials. And remember that there are hundreds of thousands of software tutorials shared online. So interfaces like Sifter can make it easier for a person to find tutorials and learn from them. Finally, we found that if we take advantage of the underlying structure of Photoshop and learn how to adapt the 3 main classes of operations, we can transfer most photo manipulation procedures. And as we all know, taking pictures has become incredibly popular these days, where we all have smartphones in our pockets. And people also really enjoy manipulating their images. There are constantly new apps that appear to perform some kind of manipulation on your images. So our work really provides a framework for all of these macros, and it also provides some techniques to make them content adaptive. So I believe that there are many interesting future research directions and open questions in the domain of instructional material. So one of the questions is, how can we apply these ideas to different domains? So as we saw at the beginning of the talk, procedural instructions appear in all kinds of different domains, but many of those are actually physical tasks that occur in the real world. And so it's easy for a person to capture a video of someone performing a physical task like cooking, but a major challenge in generating instructions for such tasks is in recognizing and segmenting the physical motion into operations. And if the goal is to make a static tutorial, a related challenge is in selecting the images to then show in the static tutorial. Given that instructions are designed for humans, another question I'm very interested in is, can we build an algorithm to automatically pass out the operations and apply them? Meaning, can we have a computer automatically follow the instructions? And so one domain we have just started looking at are sewing patterns. So websites like Birder Style contain thousands of sewing patterns like this one. And so these patterns don't write out the step-by-step instructions, but instead they implicitly describe the cutting, folding, and stitching operations that are required to make the garment. And so we are currently developing an algorithm that combines machine learning with integer programming to automatically pass such patterns into 3D models. And I'm really excited about this work because I think it opens up a lot of directions for future work. So for example, one thing you can do is you can create hybrids of past patterns in our database, or we could further analyze the pattern and transform it into a step-by-step format. We could then think of physically extending sewing machines that provides step-by-step instructions to people and also gives feedback if a person makes mistakes. So this would allow us to create physical tools that are smarter and safer. And another open question is, can we create more effective online instructions beyond procedural tasks? So one domain I'm particularly interested in are video instructions like the ones you can find on the Khan Academy. So I'm interested in applying the same approach that I've used for step-by-step instructions to online courses, meaning that I would like to study what makes these courses effective and then build a set of tools and techniques to help people create video instructions and also facilitate the learning process. So I showed you a number of projects today. In addition, I also worked on tool for media editing. I've been fortunate to work with the Berkeley School of Journalism for a couple of years, and multiple projects came out of that collaboration. And I also worked on some projects on resolution enhancement. I don't have time to cover these in this talk, but please feel free to ask me questions about them now or later. Thank you very much.
I think we have time for a couple questions.
I'm curious how reliant in the tutorials work and the tools work. Is it that the Adobe tools have an API that reveals to you kind of the high-level functions that are being called, and what would you do to do that if you were doing it on a system that didn't have that kind of information?
So our work definitely leverages the operation history, and we use that. If we didn't have that, and if we just had like a video as an input, I think it would be a lot harder. So I think you would need to try and recognize from the image and maybe train beforehand what the different operations are, and maybe build a classifier for each operation. That would be one way to go. In the case of the GIMP work, so originally this was implemented with GIMP before we moved it to Photoshop, but GIMP actually did not provide operation history at that time, and so it basically just involved me going into, since it's an open source software, it involved me going into the operations and actually write out print-out statements, but obviously this is not something that would scale. So,
did you learn like a higher level of information that you could have added or could change, for example, after you helped move to the Adobe API, that would have made it easier had it revealed something at a higher level semantically about the operations?
So the question was if there's something that I learned from the experience working with Photoshop about the information that should be provided in the histories. And I think one of the big challenges we have dealt, which was particular to Photoshop, is that Photoshop does not reveal brushstrokes in the operation history and where the brushstrokes are made. And so that was a challenge for us. We also found that the more information we have, the better it is. And so the operation history sometimes does not provide all the parameter changes or the intermediate steps that a person took. And there's actually a lot of information in if someone is trying out many different parameter settings before converging to one setting. And in this experimentation phase, there's a lot of things that others could learn from that's not present in the histories.
In your the first part of your talk, you discussed cleaning the histories to remove undos, for example.
Mm-hmm.
I can imagine contexts where undos are part of the learning, mm-hmm. that you want to demonstrate what not to do, mm-hmm. or and the like, and then back up. Have you contemplated how you would incorporate those into the method?
Yes. So the question was if undos are actually essential for the tutorial, and so. To answer that, I think you're right. So two things. First, we do expect that the person already knows what they're doing when they're making the tutorial. So the undos are usually errors, so they're not part of the intention that we have. But we also provide, in the case where you want to show in a tutorial what not to do, we also provide an interface that after effect the person can actually modify the tutorial. And mainly we provided this interface to let the person modify the text descriptions, because that's one place where our text descriptions are okay but not great. But it could also be used to go back and see which operations were deleted and add them back into the tutorial. Yes?
I'm wondering how far these can generalize. So I can imagine using or adapting your techniques, for example, for an audio manipulation program where you're doing lots of things with sound. Would it work for tutorials about Microsoft Word, or to push it further? I'm imagining it wouldn't work for LaTeX bibliographies, but where do you think the boundary is?
I think it is quite generalizable. I actually have seen people in New York using the exact same techniques for creating tutorials for Excel spreadsheets. So basically, as long as you have an operation history, the grouping techniques that we propose are also, they apply more generally. You may need to go beyond just the absolute and relative grouping, and you may need to add something to that. But I think otherwise, as long as you have the operation history, I think they are very generalizable. Yes?
So you mentioned in the parameter learning part of the talk about 20 examples to get the results you're showing, and you also showed some failure cases. And could you say, were those like along the way to 20? Is that after 20? Or can you also say something about, does it fail in a particular way, or what does it look like as you work up towards 20 or 40, right? Like why 20?
Yeah. So the question was if it's what the failure case is all about, and if there are patterns in the failure cases. And so the images that I showed you were all after 20. And so what we notice is that in the case of the contrast manipulation, the particular person who trained it really had they always did the setting differently. And so it was hard for us to learn this. And it does get better when we go beyond 20. It always gets better when we go beyond 20. But usually the difference is incremental. But for cases like the contrast manipulation and global manipulations in general, the change can be quite significant afterwards. But for other manipulations that are more targeted to semantic features in the image, like eye makeup and so on, the results usually don't get so much better after 20.
Further questions?
Thank you.
Thanks, Brian.